So now we want to prove this lemma. So basically, what's the approach we will take is that if we have this path and if we have, say, a neighbor of this P1 and say PL, a neighbor of this which is PI, and because this is longest path, we know that all the neighbor of P1 and PL are within this path. If this PL is adjacent to this, say, then again we get a long path. So not even the next vertex, but some vertex which is kind of close to this PI. Then we get this cycle. So in that case, we get a long cycle which satisfies certain condition. So we can avoid that. Once we avoid that, our situation mostly look like this. We have neighbors of B1 and neighbors of BL are mostly disjoint, and neighbors of P1 are mostly on the left and neighbors of PL are mostly on the right. But even in that case, because of the two connectivity, this left part and right part cannot be, totally separated. Then if we find some path here using the vertices outside, then what we can do is we can take these cycles. Note that this cycle contains all of neighbors of P1 and neighbors of PL, and P1 and PL as well. There could be one case, say, which is one common neighbor of P1 and PL. So this actually take care of P1, PL minus 1 plus 2, say. So we get a long enough cycle. So that's how we want to proceed. So for that, we want to first show that this graph can be, this path can be divided to this left part and right part, so that all the neighbors of PI has not bigger index than the neighbors of PL. So let P be P1 to PL, and let PIJ be PI to PJ. Let S be degree of P1 plus degree of PL, and suppose that the circumference of G is smaller than the minimum of NS. Say we call a pair IJ with I smaller than J a crossover. If PJ is a neighbor of P1 and PI is a neighbor of PL. So exactly this situation. Then if we add edges, P1, Pj, and Pi, Pl, here's a cycle of length L minus J minus I minus 1, because the number of vertices here are J minus I minus 1. So that much we miss. So we assume that the circumference is smaller than S. So this is smaller than S. And we can claim that there are no crossover. If P has a crossover, we choose one with this is I and J. Let IJ be the one minimizing J minus I. So that means any vertex between is not a neighbor of B1 and not a neighbor of BJ, BL. Also, this BL has no neighbors in, say, BR minus 1, where BR is a neighbor of B1. Because if that's the case, this is R minus 1. This together with the connectivity is a longer cycle. So that's a contradiction that we take a longer cycle P, longest cycle P. So what do we get? We get that as all the neighbor of BL lies inside of the path. So out of L, I mean, we know that the middle one, J minus I minus 1 are not neighbor. And also there are the degree of P1 many non-neighbor. So this is strictly smaller than S minus T of P1. This is smaller than S because of this. So this implies that degree of P1 plus degree of PL is smaller than S, a contradiction. Because we took S to be the sum. So this proves the claim. And now we know that the graph looks in this way. So now our goal is to find this kind of path to build up these cycles. But we cannot directly, ensure that path right away. Because, let's say, you have this. And then if, by using two connectivity, you can, say, find some passes from here to here, here to here, but that could look in this way. Then, you have to find another path and another path until it goes to inside of this territory, so that you can actually find some cycle in here, say, in this manner. So we want to keep building such passes so that we want to at the end find some cycle which kind of alternates. So this is indeed a cycle, and then which contains all the neighbors of P1 and PL. So that's our goal, to build such cycle. So let's give some name on this too. This indicates that we want the path which starts before this left point, and then we want to somehow arrive the point which is righter than this. So let's say T0 is maximum I, such that Pi is the neighbor of P1. And P is the minimum I, such that Pi is the neighbor of PL. Then we know that T0 is smaller than P, as there's no crossover. So our aim is to find a cycle which contains P1 and PL as well as all of its neighbors. Then it has length at least T P1, TPL plus 2 vertices P1 and PL, and in case these two coincide, we count one vertex twice here, so we get strictly bigger cycle than S. So we are done. Because we assume that we assume that circumference is strictly smaller than minimum of N and S, but we get a longer cycle, so contradiction. So as long as we find such cycle containing all neighbors of P1 and all neighbors of PL and P1 and PL, then we are done. So now we want to find such cycle. To find such a cycle, we iteratively define passes P1, P2, and so on. How? Given T I minus 1, we have T0. We choose integers Si and Ti with Si is smaller than Ti minus 1 and Ti is bigger than Ti minus 1, and Ti as large as possible, such that G has a path Pi from Vsi to Vti. That is internally disjoint from P. So what it means is that we choose S1 and T1 and find the path whose all internal vertices, so vertices which are not the end, the vertices of this path except the end 2 are disjoint from this path P. Such a path exists because G minus Vt0 is connected. So what it means is that you take these vertices and these vertices and you delete this one. Then this graph is connected. So we take, say, these vertices and these vertices and we delete this. In G, we have this set A and B. G is connected, so we have A and B. So there must be a path between A and B. And you take the shortest one, then that does not use any vertices in A and B except the two end. Such a path gives us, this path. And among them, we choose the one which, maximize T1. And then again, you choose S2 and T2 with satisfying same condition. And S3 and T3 satisfying same condition. And S4, T4 satisfying same condition until you get the point where this T sub R is bigger than T. So first, we know that these paths are disjoint. Because, why? If this path and this path are not disjoint, they share one vertex. say this vertex and this vertex are same. Then what you do is you go to here and then you come here. Then you get again path starts from left of T0 and arrives at right of T0, but arrives at T2, which is bigger than T1. But how did we choose T1? We choose the one which satisfies this. And then there is this path from here to here, maximizing T1. That contradicts the maximality of P1, because if we take this path, if these two vertices are same, if we take this path, then we could arrive at the further point, but we assume that this T1 is as far as we could get. So that shows that these two paths are actually disjoint. They don't share any vertex. Because, if Pi shares a vertex with, say, lateral path Pj, then we can choose Pi as a path from Psi to Ptj, which contradicts the maximality of Ti. Similarly, Si plus 1 is bigger than Ti minus 1. What do you mean is that this S3 is on strictly right hand side than T1. I mean, could be same, but it's not on the left. Since otherwise, Ti plus 1 would be chosen instead of Pi. What it means is that if we have S1 to T1, and then this is T0, and S2 to T2. If here we have S3 to T3, then this T3 is bigger than T2. But if T3 is still smaller than T1, then this also satisfies, S3, let's say this is just A, B. A is, between T1 and B is further than T2. So this satisfies the condition of this. So this path is actually better path than this P2. So instead of P2, we would have chosen this, so which is a contradiction of the maximality of this T2. So we have this condition, this property. So let R be the smallest index such that T sub R is bigger than P. And let A be the minimum J such that Pj is the neighbor of Vi and J is actually bigger than S1. So this is the vertex, this vertex A. No, sorry. This is actually this vertex A. And we will call this vertex B. P is maximum of J such that Bj is neighbor of Bl and J is smaller than Tr. This is B. Because, so that's exactly in here we have this is A and this is B. So this A could be T0 and B could be P. Since S1 is strictly smaller than T0 and TR is strictly bigger than P, T0 and P satisfy this condition. So there are at least one thing satisfy this condition. So we take A as minimum and B as maximum. So they are well defined. So now say when R is odd, the two passes you take B1 and you jump to BA. So in this case, this is actually even. So how do you do it? Is you take this pass and then this path together to get a cycle. And for odd one, let's write A S2 P2 P T2 to S4 P4 up until to TR minus 1 P and add HP VB and VL. And another path from 1 to S1, P1, T1 to S3, P3, up until to PR, P, T sub R, L. You can draw yourself that, let's say this is T0, this is P1, P2, P3, and this is A, this is B. And what it says is that you take this and A to S2, P2, and up until to here. And then you take this and this. This is one path. And the next path is 1 to S1 and take P1. And then T1 to S3. And then P3 up until to PR. And then once you arrive this TR, then you take to L. Then you get this cycle. When R is even, you do in similar way, but slightly, careful on the other end. Say when R is even, take the path starting with P1 VA, which is say TR, and ends with P TRL, while the other end path, which is PB and ends with PB PL. So you start with this goes to here and then take this P TRL, while the other path, which is use this and use this edge to end. As Si plus 1 is at least Ti minus 1. Hence, we know the S1 is strictly more than A, and this is at most T0, S2, T1, S3, T2, TR minus 1, Q, no, not Q, P, TR. So this implies that concatenation of two passes above they are actually paths, okay? The concatenation of the passes are actually a path. And their union is a cycle. So by the definition of A, what do we know? We know that neighbor of B1 is all in either this first part or this part. S1, between S1 and A, there are no neighbor, and then all of neighbor are either here or here. Both are included. And similarly, neighbor of PL is in this part. So the cycle includes all the neighbors and P1 and PL, hence has length bigger than S, a contradiction. So this proves the Bound's lemma. So using this, we can prove long cycle version of Euler's theorem, which implies the long cycle version of Direct theorem as well. Let G be a two connected n vertex graph. If degree of U plus degree of V in G sums up to at least S whenever UV is a non-adjacent pair in G, then circumference of G is at least minimum NS, minimum out of N and S. So let's prove this. So if S is at least N or N, then we already know Euler's theorem. So assume S is strictly smaller than N. And suppose P is a longest path in G with endpoints X and Y. And we know that since G is connected, and we assume that the graph is non-Hamiltonian, then maximality of P implies XY is not an edge. Because otherwise, if we have a edge, then P with this edge forms a cycle, and then that's a cycle, non-Hamiltonian cycle. So there is some vertex outside. Then connectivity implies that there is an edge. So this yields a longer cycle, longer path. So what do we know? This is not an edge. So we have the condition implies the summation of the degrees at least S, and Bound's lemma is the conclusion. Yeah. And someone like the quartile theorem, let's prove one more, degree least version of theorem regarding long cycle. So again, let G be two connected graph with degree least T1 to Tn in non-decreasing order. Non-decreasing order. If G has no non-adjacent vertices x and y with degree of x is I and degree of y is j, such that degree of I is less than or equal to I. D sub I is less than or equal to I, and D sub j plus 1 is less than j, less than or equal to j, and I plus j is smaller than s. Then the circumference is at least s. If there are no non-adjacent vertices satisfying all this, then we get this. So let's prove this. So among all longest paths in G, again we choose P1 to PL, our longest path with maximum degree sum of the vertices at the end. And if the degree sum is at least s, then Bondi's lemma implies the conclusion. So what we need to show is that we want to show that if the degree sum is smaller than s, then it violates the hypothesis. So we show that. So as G is connected, if you get a cycle again, then we get a longer path. So we know that P1 PL is not on H, because again by same logic, if there is an H, then we can find the H towards the outside that give us a longer path. Let I be the degree of V1 and degree of VL be J, so that the I is smaller than or equal to J. What do we know? We know that all neighbors of V1 and VL lie in this path. And if VR is a neighbor of V1, then we know this is another longest path. VR minus 1 to V1, VR to VL is another longest path ending at VL. So this vertex must have a smaller degree than V1. So now what we want to show is, we want to show this. So we want to find the many vertices, I vertices with degree less than x which is the end vertex, so P1. So this provides some vertices with degree less than V1. So degree of Vr minus 1 is at most degree of V1, which is I, by the choice of P. This holds for all neighbors of V1. So this yields I vertices with degree at most I, including P1. So Ti is at most I. So note that V2 is a neighbor of V1. So trivially, it said, so R equal to satisfy. So this condition says that V1 is at most P1. So there are I vertices, including Vi itself, satisfying this. So we get this condition. Similarly, there are J vertices other than Vi, P1, having degree at most J. And we know that P1 itself has degree I, which is at most J. So there are at least J plus 1 vertices with degree J. So this satisfies. And what do we know? By the hypothesis, I plus J is degree of X, degree of P1 plus degree of PL is smaller than S. So that's exactly how this condition is forbidding contradiction. So this proves this theorem. And yeah, so today we learned about the circumference and then several theorems, giving the conclusion that the graph has a long cycle, meaning it has large circumference. So yeah. Thank you for listening.